while astronomers celebrate interstellar visitor 3I Atlas as the most exotic object we've ever studied, a far stranger mystery is unfolding 18 astronomical units from the Sun. The strangest comet in the solar system isn't some interstellar wanderer from another star. It's been orbiting quietly between Saturn and Uranus for billions of years, and we only just realised how bizarre it truly is. 2060 Chiron is surrounded by rings that exist in a zone where physics says they should have collapsed into moons millions of years ago. Yet there they are, organised, evolving, defying explanation. Even stranger, Chiron is venting primordial gases, propane and methane, like some ancient time capsule slowly opening before our eyes. Stay with me until the end, because what's happening around this tiny world might be the birth of a moon, happening right now on human timescales. If the Chiron mystery has pulled you in the way it has me, go ahead and hit that like button and subscribe so you're here when the next observation changes everything we think we know. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think we're finally seeing the full picture of what's really happening out there. Part 1, the bombshell. Chiron, not 3I Atlas, is the real outlier. Everyone loves a visitor from beyond. When interstellar comet 2, Borisov, swept through our solar system in 2019, the world went wild. Here was proof, they said, that we could actually catch objects from other star systems passing through our cosmic neighbourhood. Then came 3I Atlas in 2025, another traveller from the void between stars, and suddenly it seemed like we were living in a golden age of interstellar discovery. The headlines screamed about alien chemistry, exotic ices, objects that had never felt our sun's warmth until their brief, fateful encounter with our little corner of the galaxy. But here's the thing nobody's talking about. While everyone was looking up, squinting at these distant visitors, scanning the sky for the next interstellar interloper, the weirdest object in our entire solar system was hiding in plain sight. It's been here all along. We've known about it since 1977, and it's so strange, so fundamentally bizarre, that it makes those interstellar comets look downright ordinary by comparison. Its name is 2060 Chiron, and it is, without exaggeration, one of the most mysterious objects we have ever studied. Chiron isn't just a comet, it isn't just an asteroid, it's something in between, something we call a centaur named after the mythological creatures that were half human, half horse. These objects orbit in the chaotic space between Jupiter and Neptune, a gravitational no-man's land where nothing stays put for long. They're thought to be ancient refugees from the Kuiper Belt, kicked inward by gravitational encounters with the giant planets, doomed to wander until they either get ejected from the solar system entirely or crash into something. They're transitional objects caught between worlds, neither fish nor fowl. But even among centaurs, Chiron is an outlier. For decades we thought we had Chiron figured out. It was discovered by Charles Cowell at Palomar Observatory, initially classified as an asteroid, then reclassified as a comet when astronomers noticed it had a coma, that fuzzy cloud of gas and dust that surrounds active comets. Fine. Problem solved. It's a comet that looks like an asteroid sometimes. Move on. Except we couldn't move on because Chiron refused to behave. In 2011, astronomers observed something impossible. During a stellar occultation, when Chiron passed in front of a distant star, the starlight didn't just blink out once as the body crossed in front of it. It flickered. Multiple times. Symmetrically. As if something was surrounding Chiron, blocking the light in patterns that suggested structure. At the time, most researchers chalked it up to jets or debris clouds, the kind of messy, temporary features you'd expect from an active comet. But then came 2022, then 2023, and with each new occultation, each new observation, the picture grew stranger and more impossible to ignore. By September 10th, 2023, after a multi-chord stellar occultation campaign led by teams at the Instituto de Astrofísica de Canarias, the truth became unavoidable. Chiron isn't surrounded by random debris, it's surrounded by rings, multiple rings, at least 3 distinct narrow rings at approximately 273 kilometres, 325 kilometres, and 438 kilometres from Chiron's centre. And beyond those, something even more baffling, a faint diffuse feature at roughly 1,380 kilometres out. Let that sink in for a moment. Chiron, a comet barely 200 kilometres across, has a ring system. Not one ring, multiple rings, organised, structured, confined rings that circle this tiny ancient object, like miniature versions of Saturn's famous bands. This isn't supposed to happen. Ring systems belong to giant planets: Saturn, Jupiter, Uranus, Neptune. These are massive worlds with enormous gravitational wells, capable of capturing and organising debris into stable, long-lived structures. A few small bodies in the outer solar system have rings, sure. Chariklo, another centaur, has 2 narrow rings. Haumea has 1. But those are simpler systems, easier to explain away as recent collisions or disrupted satellites. Chiron's rings are different. They're complex, they're multiple. They're confined into narrow bands despite having no obvious mechanism to keep them from spreading out into a shapeless cloud. And here's the real kicker. At least one of those rings, possibly more, exists outside Chiron's Roche limit. The Roche limit is the boundary inside which tidal forces tear objects apart. It's the reason Saturn has rings instead of a single massive moon circling where the rings are now. Material inside the Roche limit can't clump together, because gravity pulls harder on the near side than the far side, ripping apart anything that tries to form. Outside the Roche limit, material should be able to aggregate, to stick together, to form moons. Chiron's outer rings are sitting right in the zone where they should have collapsed into satellites millions of years ago, but they haven't. They're still there, still orbiting, still structured, defying every expectation we have about how small bodies work. And it gets stranger, because Chiron isn't dead, it's active, it's venting gas, it's changing. This isn't some frozen relic from the early solar system, locked in stasis for 4.5 billion years. This is a live system, a miniature planetary laboratory where something impossible is happening right now, in real time, and we're only just beginning to understand what we're looking at. So while the world chases interstellar visitors, while headlines trumpet the latest exotic chemistry from objects that will never return, the real mystery is right here. It's been here all along, and it's about to rewrite what we thought we knew about comets, rings, and the hidden chaos lurking in our own backyard. Part 2, The Data That Broke the Model, 2020-2025, Occultations and JWST. Stellar occultations are one of astronomy's most elegant tricks. You wait for an object to pass in front of a distant star, then watch how the starlight changes. If the object has an atmosphere, the star dims gradually. If it has a moon, you get an extra dip. If it has rings, you get a pattern, a signature written in flickering starlight that tells you exactly where material is orbiting and how much of it there is. It's like reading Braille in the sky. For Chiron, the occultation on December 15th, 2022 was supposed to be routine. Teams across multiple continents positioned telescopes along the predicted shadow path, ready to record the brief moment when Chiron would block light from a background star. What they got instead was a data set that made no sense. The starlight didn't just dim once. It showed a broad, extended dimming centered on Chiron, stretching out to a radius of about 580 kilometers. That alone was weird. Chiron's nucleus is only about 220 kilometers across, so what was causing this massive shadow? But even stranger were the sharp, distinct dips within that broad profile. 2 narrow features at approximately 325 kilometers and 423 kilometers from Chiron's center. The initial interpretation was cautious. Maybe these were dense regions within a larger debris disk. Maybe they were temporary structures, shells of material blown out during an outburst. But when the team analysed the geometry and the sharpness of the features, they realised something astonishing. At least one of these structures lay outside Chiron's Roche limit. Material that should have clumped into a moon was still sitting there, organised into a ring, as if gravity had forgotten how to work. Then came the September 10th, 2023 occultation. This time, observers captured multiple chords across different locations, giving them a 3-dimensional view of whatever was surrounding Chiron. The results were published in the Astrophysical Journal, and they were unambiguous. 3 distinct rings. Not debris clouds, not transient shells. Rings! The geometry was precise. The rings were coplanar, meaning they all orbited in the same plane, tilted relative to Chiron's orbit. The pole of this ring system pointed toward ecliptic coordinates of roughly 151 degrees longitude and 20 degrees latitude, give or take about 6 degrees. This wasn't random. This was an organised system, something with structure and stability, something that had been there long enough to settle into a coherent configuration. And then there was that faint outer feature at 1,380 kilometres. Too diffuse to be a ring in the classical sense, but too structured to be random dust. Something was out there, something we still don't fully understand. But occultations only tell you where the material is. They don't tell you what it's made of. For that, you need spectroscopy. In July 2023, the James Webb Space Telescope turned its near-infrared spectrograph toward Chiron. JWST observed Chiron for hours, mapping its surface and the faint coma surrounding it across wavelengths from 0.97 to 5.27 microns. What it found was astonishing. Chiron's surface is covered in ices. Not just water ice, though, there's plenty of that. Mostly in an amorphous, disordered state. There's carbon dioxide ice, carbon monoxide ice. And then things get really interesting. JWST detected ethane, propane, acetylene. These are light hydrocarbons, organic molecules that form in the outer solar system, but are usually buried deep inside cometary nucleon, locked away in the ice matrix. On Chiron, they're right there on the surface. But the biggest surprise was methane. JWST didn't just detect methane ice, it detected methane in a non-local thermal equilibrium state, fluorescing under sunlight in a way that indicated active outgassing. Methane was being released from Chiron's interior, venting into space, creating the coma that gives Chiron its cometary appearance. In January 2024, JWST went back for a follow-up observation as part of Cycle 2. This time, the goal was to measure production rates and map where the gas was coming from. The results were stunning. Chiron was producing approximately 1.6 times 10 to the 27th molecules of methane per second. That's a staggering amount of gas for such a small object. Carbon dioxide production was lower, around 1 times 10 to the 26th molecules per second, but still significant. Even more intriguing, the spatial mapping showed that methane and carbon dioxide were coming from different regions of Chiron's surface. They weren't being released uniformly. Something about Chiron's internal structure, its composition, its thermal state, was causing different volatiles to vent from different locations. And here's the kicker: carbon monoxide gas, which many models predicted should be one of the dominant outgassing species, was not detected above the noise level. It wasn't there, at least not in the amounts anyone expected. What does this all mean? It means Chiron is far more complex than we thought. The occultation data showed rings that shouldn't exist. The spectroscopy showed a surface composition that doesn't match any simple comet model. And the outgassing patterns showed internal differentiation, regions of different temperature or composition that are driving activity in ways we still don't fully understand. Taken together, these observations force a rethinking. Chiron isn't a comet with rings. It's not an asteroid with a coma. It's something else entirely, something we don't have a good name for yet. A hybrid system. A planetary embryo that never grew up. A laboratory where the rules of small-body physics are being written in real time. Part 3. Activity where there should be none. The amorphous ice trigger. Chiron orbits the Sun at a distance of about 18 to 19 astronomical units. To put that in perspective, Earth orbits at 1 AU, Jupiter at 5, Saturn at 9.5. Chiron lives way out there, in the cold and the dark, where sunlight is feeble and temperatures hover around 80 to 100 Kelvin. That's roughly negative 190 to negative 170 Celsius. Cold enough that nitrogen freezes solid, cold enough that methane is ice, not gas. And yet, Chiron is active. It has a coma. It vents gas. It behaves like a comet, even though it's far too cold and far too distant for the classic comet model to work. Normally, comets become active when they get close to the Sun and solar heating warms their icy surfaces enough to sublimate the volatiles. Water ice starts sublimating around 3 AU. Carbon monoxide can sublimate farther out, maybe around 10 to 15 AU if conditions are right. But Chiron is active at 18 AU. That shouldn't be possible with solar heating alone. So what's driving it? The leading hypothesis is something called the amorphous to crystalline ice phase transition, and it's one of the coolest processes in planetary science. Water ice can exist in 2 states: crystalline, where the molecules are arranged in an orderly lattice, and amorphous, where they're frozen in a disordered glassy state. Amorphous ice forms when water vapour condenses very rapidly in extremely cold conditions, like in the outer solar system or in interstellar space. The thing about amorphous ice is that it's not stable. It wants to crystallize, and when it does, it releases energy. Not just a little bit, a lot. Enough to warm the surrounding material, potentially triggering a runaway heating event. Even more importantly, amorphous ice can trap other gases inside its structure. Methane, carbon monoxide, carbon dioxide. These volatiles get locked into the disordered ice matrix, held prisoner until the ice crystallizes and releases them. The phase transition happens at around 61 Kelvin. Chiron's surface temperature hovers right around that threshold. Depending on where you are on the surface, depending on the season, depending on Chiron's eccentric orbit, parts of the surface could warm just enough to trigger crystallization. When that happens, all hell breaks loose. The trapped gases are suddenly released, pressure builds, the ice matrix fractures, material gets blown off the surface, venting into space, creating jets and outbursts. And here's the key point. This process doesn't need sunlight. It's driven by internal heat release. Once it starts, it can propagate through the interior, crystallizing deeper layers, releasing more gas, creating a self-sustaining cycle. This could explain Chiron's activity. It could also explain something else, the rings. In 2022, astronomers noticed that Chiron had experienced a brightness outburst between March and September of 2021. Its magnitude increased by about 0.6, a significant jump that indicated a major release of material. If that material was launched with enough velocity, if it was vented from the right location on Chiron's surface, it could have gone into orbit. It could have joined the existing ring system, resupplying it, adding fresh material to replace whatever was being lost to collisions or gravitational perturbations. In other words, Chiron's rings might not be ancient. They might be constantly renewed. Chiron could be venting material into orbit on a regular basis, maintaining its ring system through periodic outbursts driven by this internal ice engine. Think about that for a moment. This isn't a static ring system left over from some ancient collision. This is a dynamic, evolving structure, fed by an active process happening right now, today, as Chiron tumbles through space. It's a self-regulating system, a built-in renewal mechanism that explains why the rings persist despite all the reasons they shouldn't. But here's where it gets even more interesting. The amorphous ice hypothesis is just that, a hypothesis. We don't know for sure that this is what's happening. There could be other processes at work. Cryovolcanism, where internal heat drives volcanic eruptions of icy slush. Mechanical fracturing, where Chiron's tumbling rotation stresses the crust and opens cracks that release trapped gases. Impact-driven lofting, where small meteoroids hit the surface and kick up debris. Maybe it's all of the above. Maybe Chiron has multiple engines, multiple sources of activity, each contributing to the ring system in different ways. We don't know yet. What we do know is this. Chiron is not a frozen relic. It has an internal life, a geologic heartbeat, something driving change and evolution on timescales we can actually observe. This isn't a museum piece. It's a living system, and that makes it one of the most scientifically valuable objects in the entire solar system, because we're not just studying what it was, we're studying what it's becoming. Part 4. The Roche limit violation. Why the outer rings should not exist. The Roche limit is named after Edouard Roche, a French astronomer who calculated it in the 1850s. The concept is simple but profound. Imagine you're a small moon orbiting a planet. Gravity holds you together, right? Your own self-gravity keeps all your rocks and ice bound into a cohesive body, but you're also feeling the gravitational pull of the planet you're orbiting. And here's the thing, that pull isn't uniform. The side of you facing the planet feels a stronger tug than the side facing away, because it's closer. This difference in gravitational force is called a tidal force. If you orbit close enough to the planet, those tidal forces become stronger than your own self-gravity. At that point, you can't hold yourself together anymore. You get stretched, pulled apart, ripped into pieces. The debris spreads out into a ring. That critical distance where tidal forces equal self-gravity is the Roche limit. For large solid bodies, the Roche limit is about 2.4 times the planet's radius. For looser, rubble pile objects, it's closer to 3 times the radius. Inside that limit, you get rings. Outside that limit, you get moons. This is why Saturn has rings. Material orbiting inside Saturn's Roche limit can't clump together. It just spreads out into those beautiful bands we all know. Material outside the Roche limit forms moons like Mimas, Enceladus, and Titan. Now apply this to Chiron. Chiron's radius is about 110 kilometers, give or take. Its Roche limit, depending on the assumptions you make about density and the strength of the material, should be somewhere around 200 to 300 kilometers from its center. The outer ring at 438 kilometers, outside the Roche limit, the faint feature at 1,380 kilometers, way outside the Roche limit. These structures should have collapsed into moons millions of years ago. The particles should have stuck together, accreting into larger and larger clumps until they formed one or more satellites orbiting Chiron. But they didn't. They're still there, still in ring form, still defying the basic physics we use to explain every other ring system in the solar system. Why? Part of the problem is that Chiron isn't a nice simple sphere. It's triaxial, meaning it's elongated, shaped more like a lumpy potato than a ball. That complicates the Roche limit calculation. The gravitational field around a triaxial body isn't uniform. There are regions where gravity is stronger, regions where it's weaker, and those variations can stabilize or destabilize orbits in unexpected ways. In 2025, a team led by Madeira, Morgado, Pereira, and others published a dynamical simulation study that modelled test particles orbiting around Chiron, taking its triaxial shape into account. They found something fascinating. Close to Chiron, inside about 260 kilometers, the environment is chaotic. Particles don't survive for long. They either crash into Chiron or get flung out into space within a few years. But beyond 260 kilometers, things stabilize. Particles can survive for a decade or more, maybe longer. The simulation showed that Chiron's irregular shape creates zones of relative stability where rings can persist. The researchers also found hints of something called spin-orbit resonances. These are special orbital configurations where the particle's orbital period is related to Chiron's rotation period by a simple ratio, 1 to 3, 1 to 5. These resonances can act like invisible shepherds, confining particles into narrow bands, preventing them from spreading out. Two of Chiron's rings, nicknamed Chi2R and Chi3R, might be sitting right in these resonance zones. If that's true, then the rings aren't being held together by moons. They're being held together by Chiron's own gravity, mediated through these resonance effects. But here's the problem. We don't see any shepherd moons. In every other ring system we know, Saturns, Jupiters, Uranuses, narrow rings are confined by small moons orbiting just inside and outside the ring. These shepherd moons gravitationally herd the ring particles, keeping them from spreading out. Without shepherds, rings diffuse. They dissipate. They don't stay narrow and organized. So where are Chiron's shepherds? Maybe they're there, but too small to detect. Maybe they're dark, low-albedo objects that don't reflect enough light for our telescopes to see. Or maybe they don't exist. Maybe Chiron's rings are young, formed only recently, within the last few decades, and haven't had time to form moons yet. Or maybe something else is going on. Maybe Chiron's tumbling, chaotic gravity field is somehow suppressing aggregation, preventing particles from sticking together even outside the Roche limit. Maybe the outgassing, the constant venting of gas and dust, is disrupting the accretion process, keeping everything stirred up and preventing clumping. We don't know, and that's what makes this so exciting. Chiron is forcing us to rethink everything we thought we understood about ring dynamics. If our models are wrong for irregular bodies like Chiron, then they might be wrong for other small bodies too. Asteroids, Kuiper belt objects. Maybe ring formation is far more complex, far more nuanced than we ever imagined. And maybe Chiron is giving us a front row seat to that complexity, showing us what happens when a small body tries to grow a satellite system and fails, or succeeds, or gets stuck in some strange intermediate state we've never seen before. Part 5. The real-time evolution, a changing system on human timescales. Planetary science usually requires patience. Geological processes take millions of years. Orbital evolution takes billions. If you want to study how planets form, how moons accrete, how ring systems evolve, you dig through data from ancient impact craters or analyze isotope ratios that tell you what happened 4.5 billion years ago. You reconstruct the past from clues left in the present. But Chiron doesn't care about patience. Chiron is changing right now. The occultation record for Chiron spans multiple epochs: 2011, 2018, 2022, 2023. Each observation gives a snapshot of the ring and disk environment at that moment in time, and when you compare those snapshots, you see differences. Not subtle, maybe. It's just noise differences. real, measurable changes in the structure and density of the material surrounding Chiron. The 2023 data showed features that weren't present, or at least weren't as prominent, in earlier observations. Asymmetries in the ring structure, possible expansion of the broad disk that extends beyond the narrow rings, density shifts that suggest material is moving, reorganizing, responding to forces we haven't fully identified yet. Then there's the outburst. Between March and September of 2021, Chiron brightened by about 0.6 magnitudes. That's a huge change, easily visible from Earth, indicating a major release event. Dust and gas were vented into space, possibly enough to resupply the entire ring system. Now ask yourself this question. What if we're not just studying a ring system? What if we're watching a moon form? Think about it. Chiron is venting material. That material goes into orbit. It collides, it sticks, it slowly aggregates. Over time, larger and larger clumps form. Eventually, if conditions are right, those clumps become moonlets. The moonlets become moons. We go from a ring system to a satellite system. This process is thought to take millions of years. It's how Saturn's moons formed. It's how Earth's moon might have formed after the giant impact that created it. It's a slow, gradual process, impossible to observe directly. Except maybe not. Maybe on Chiron it's happening faster. Maybe the constant outgassing, the repeated injection of fresh material, is accelerating the process. Maybe we're watching the first stages of satellite formation, compressed into decades instead of eons. Or maybe the opposite is true. Maybe the rings are ephemeral, a transient phenomenon that only appears when Chiron is active. Maybe when the outgassing stops, the rings dissipate, falling back onto the surface or drifting away into space. Maybe we just happen to catch Chiron at the right moment, during a brief window when it has rings, a window that will close in another decade or century. We don't know, but here's what we do know. We can find out. We can keep watching. We can coordinate more occultation campaigns, more telescope observations, more spectroscopic studies. We can track Chiron year by year, orbit by orbit, and see what happens. No other small body in the solar system gives us this opportunity. Most asteroids are dead, unchanging. Most comets are too far away or too faint to study in detail, but Chiron is close enough, bright enough, and active enough that we can monitor it continuously. It's a natural laboratory, a planetary-scale experiment in satellite formation, ring dynamics, and small body evolution. And it's happening on human timescales, fast enough that a single generation of astronomers can watch it unfold from beginning to end. That's not just scientifically valuable, that's unprecedented. Chiron isn't static. It's alive, reshaping itself before our eyes, challenging every assumption about small body, physics, and if we pay attention, if we invest the time and resources to study it properly, it might just teach us things we never thought possible about how worlds are born. Part 6. The uncomfortable question. Who says Chiron has only one engine? The amorphous ice hypothesis is elegant. It explains a lot. But here's the uncomfortable truth. Nature is rarely that simple. Scientists love clean explanations. One cause, one effect. Chiron vents gas because amorphous ice is crystallizing. The rings exist because outbursts inject material into orbit. Case closed. Publish the paper. Move on to the next mystery. But what if there's more than one engine driving Chiron's activity? What if multiple processes are happening simultaneously, each contributing to the chaos in different ways? Consider cryovolcanism. We know it happens on other icy worlds. Enceladus, Saturn's tiny moon, has geysers that shoot water ice hundreds of kilometers into space. Triton, Neptune's largest moon, has nitrogen geysers. Europa probably has subsurface oceans that occasionally break through the ice crust. These aren't driven by ice phase transitions. They're driven by internal heat, tidal flexing, radioactive decay, processes that generate enough energy to melt or mobilize icy material and force it to the surface. Could Chiron have something similar? It's small, sure, but it's also old, and it's been wandering through the solar system for billions of years. Maybe it has pockets of residual heat trapped in its interior. Maybe tidal interactions with Saturn or Uranus during past close encounters left thermal scars that are still slowly releasing energy. Maybe radioactive isotopes, long-lived elements like potassium-40 or thorium-232, are generating heat deep inside. If cryovolcanic vents exist on Chiron, They could be contributing to the outgassing, adding methane and carbon dioxide to the mix, independent of any surface ice crystallization. Then there's mechanical fracturing. Chiron is tumbling. Its rotation is chaotic, not locked into a nice stable spin. That means stresses are constantly changing across its surface. Over time, those stresses build up. Cracks form, faults propagate. And when those cracks reach pockets of trapped volatiles, pressure is suddenly released. Gas vents out, carrying dust and ice with it. This is a purely mechanical process. It doesn't require phase transitions or internal heat. It just requires a brittle crust and trapped gas, both of which Chiron almost certainly has. Impact-driven lofting is another possibility. Chiron is out in the Kuiper Belt migration zone, a region filled with debris. Small meteoroids, bits of rock and ice left over from the solar system's formation, are constantly pelting everything out there. Most impacts are tiny, leaving no trace, but occasionally a larger one hits. The impact energy vaporizes ice, kicks up debris, and launches material into space. If the impact happens in the right place, if the ejected material has the right velocity, it goes into orbit. It joins the ring system. We know this happens. We've seen it on our own moon. Meteoroid impacts create transient clouds of dust and gas that can persist for hours or days. On Chiron, with its weaker gravity, those clouds could last much longer. They could coalesce into temporary rings or disks. And then there's the wild card, micro-moonlet interactions. What if Chiron does have small satellites, moonlets only a few kilometres across, too dark and too small for us to have detected yet? Those moonlets would gravitationally stir the ring system, creating waves, gaps, and density variations. They might even collide with larger ring particles occasionally, grinding them down into dust, creating the diffuse outer feature we see at 1,380 kilometres. Each of these mechanisms on its own could contribute to Chiron's activity. But here's the real question. What if they're all happening at once? What if Chiron is a multi-engine system, where amorphous ice crystallizes in some regions, cryovolcanic vents erupt in others, fractures release gas in still others, and impacts stir everything up periodically? That would explain the complexity. It would explain why the outgassing isn't uniform, why methane and carbon dioxide come from different locations, why the ring structure changes over time. It would mean Chiron isn't just one thing. It's a hybrid, a composite, a chaotic blend of processes that we're only beginning to untangle. If that's true, then predicting Chiron's future becomes nearly impossible. Multiple engines mean multiple feedback loops, multiple triggers, multiple outcomes. The ring system's evolution wouldn't follow a simple trajectory. It would shift and change depending on which engine is dominant at any given moment. And that's both frustrating and exhilarating. Frustrating because it means we can't just write down one equation and solve for the answer. Exhilarating because it means Chiron is even stranger, even more dynamic, even more alive than we thought. So who says Chiron has only one engine? Maybe nobody should. Maybe the real mystery is figuring out how many engines there are and how they all work together to create the impossible object we see today. Part 7. The Shepherd. Moonlet Hypothesis. Structure without a shepherd. Every planetary scientist knows the story of Saturn's rings. Those beautiful, intricate bands aren't just random collections of ice and rock. They're organised. Some rings are narrow, only tens of kilometres wide, but stretch millions of kilometres around the planet. How do they stay so narrow? How do they maintain those sharp edges? The answer is shepherd moons. Tiny satellites, sometimes only tens of kilometres across, orbit just inside and outside narrow rings. Their gravity tugs on ring particles, keeping them confined, preventing them from spreading out. It's like cosmic sheep herding, and it works beautifully. Pan shepherds the Enki gap. Prometheus and Pandora herd the F ring. Daphnis carves waves in the Keeler gap. Without these moons, Saturn's most dramatic ring structures would blur and diffuse within a few million years. So when we found narrow rings around Chiron, the obvious question was, where are the shepherds? We haven't found them. Multiple occultations, multiple observations, and no confirmed detection of any satellites around Chiron. That doesn't mean they're not there. They could be small, they could be dark, they could be in orbits that make them hard to spot. But the fact that we haven't seen them yet is a problem. Because if Chiron's rings don't have shepherds, how are they staying narrow? One possibility is that the shepherds are just too small to see. Chiron's environment is chaotic. It's dusty. It's got outgassing. Any tiny moonlet embedded in that environment would be incredibly hard to detect. It would be like trying to spot a single pebble in a snowstorm. We might not see it until we send a spacecraft there. But there's another possibility, one that's far more intriguing. What if Chiron doesn't need shepherds? What if its own irregular gravity field is doing the job? Remember, Chiron isn't a sphere, it's triaxial, elongated, lumpy. That means its gravitational field isn't uniform. There are regions where gravity is slightly stronger, regions where it's slightly weaker, and those variations change as Chiron rotates. This creates a constantly shifting landscape of gravitational potential, a dynamic environment where particles experience forces that are far more complex than simple inverse square law gravity. The 2025 dynamical simulations by Madeira and colleagues explored this. They modelled thousands of test particles orbiting around Chiron's irregular shape and tracked their orbits over time. What they found was fascinating. The inner region, inside about 260 kilometres, is a gravitational blender. Particles don't last long, they either crash or get ejected. But farther out, things stabilise. Not uniformly, though. There are zones of relative stability interspersed with zones of chaos, and critically, some of those stable zones correspond to spin-orbit resonances, places where the particle's orbital period is a simple multiple of Chiron's rotation period. Chi2r and Chi3r, two of Chiron's narrow rings, might be sitting right in those resonance zones. If that's true, then the rings are being confined not by moons, but by Chiron's own gravity, mediated through resonance effects. It's a self-shepherding system, a gravitational trick that keeps the rings narrow without needing external help. This would be unprecedented. No other known ring system works this way. But Chiron is small enough, irregular enough, and active enough that it might just pull it off. There's another piece of the puzzle: outgassing. When Chiron vents gas, that gas doesn't just disappear, it drags dust with it. The dust spreads out, forming a temporary disk or cloud. Over time, that dust settles back down, coalescing into denser regions, possibly forming or resupplying the rings. If the outgassing is episodic, if it happens in bursts tied to Chiron's rotation or orbital position, then each burst could inject material preferentially into certain orbital zones. Over time, those zones accumulate more material than others, creating the appearance of narrow rings even without shepherds actively confining them. It's a dynamic equilibrium, constantly fed by outgassing, constantly shaped by Chiron's irregular gravity. The rings would be transient on long timescales, but self-renewing on shorter ones. They'd look stable when we observe them, but they'd actually be in constant flux, maintained by ongoing processes rather than ancient, frozen-in structures. The observational challenge is enormous. To test these ideas, we need to detect those hypothetical tiny moonlets, if they exist. We need better constraints on Chiron's shape, rotation, and mass distribution. We need more occultations to track changes in ring structure over time. We need spacecraft missions that can image the system directly, resolve individual ring particles, map the gravitational field. None of that is easy. Chiron is far away, it's faint, it's moving. Coordinating ground-based occultation campaigns requires perfect timing, perfect weather, and perfect luck. Getting a spacecraft there would take years, possibly decades, and enormous funding. But the scientific payoff would be immense. If Chiron really is shepherding its own rings through resonance and irregular gravity, that mechanism could apply to dozens of other small bodies we haven't studied yet. It could explain how ring systems form and persist on objects too small to have traditional shepherd moons. And if we do find shepherds, tiny moonlets hiding in the chaos, that would be just as exciting. It would mean Chiron is even more complex, even more Saturn-like than we thought. A miniature ringed world with its own retinue of satellites, all crammed into a system barely half the size of the Earth's moon. Either way, the mystery is profound. Chiron has structure where it shouldn't. It has narrow rings without obvious shepherds. It defies the classical models, and in doing so, it's pointing us toward new physics, new mechanisms, new ways of thinking about how matter organizes itself in space. The shepherd moonlet hypothesis isn't dead, but it's no longer the only game in town, and that's what makes Chiron so scientifically valuable. It forces us to consider alternatives, to think creatively, to question assumptions we didn't even know we were making. Part 8. The Big Picture. What Chiron means for Kuiper belt migration physics. Chiron is an exile. It wasn't born where it is now, in the chaotic region between Saturn and Uranus. No object forms there. The orbits are too unstable, the gravitational perturbations too strong. Anything born in that zone gets kicked out within a few million years, either ejected into interstellar space or sent crashing into the sun. Chiron came from somewhere else. Most likely it came from the Kuiper Belt, that vast reservoir of icy bodies beyond Neptune's orbit. The Kuiper Belt is where comets are born, where the solar system's primordial material still lingers in relatively pristine form, frozen in place for 4.5 billion years. But the Kuiper Belt isn't static. Gravitational interactions with Neptune slowly perturb objects, changing their orbits, nudging them inward. Some of those objects become centaurs, entering the gravitational playground of the giant planets, beginning a chaotic journey that will eventually end in destruction, ejection, or transformation into Jupiter family comets. Chiron is on that journey right now. Its current orbit has a lifetime of only about 1 million years, a cosmic blink of an eye. Eventually it will have a close encounter with one of the giants, and that encounter will either throw it out of the solar system entirely or send it plunging inward, where it will become a short-period comet, vaporizing itself as it repeatedly dives close to the sun. But right now, in this brief window of cosmic time, Chiron is something in between. It's not a pristine Kuiper Belt object anymore. It's been warmed, activated, transformed by its journey inward. But it's not yet a full-blown comet either. It's a hybrid, a transitional form, and that makes it incredibly valuable for understanding the evolutionary pathway from Kuiper Belt object to comet. Here's the big question. Is Chiron unique, or is this a common stage? Are there dozens, hundreds, maybe thousands of other centaurs out there with ring systems, just like Chiron, that we haven't detected yet because we haven't looked hard enough or gotten lucky with occultations? There are only about 500 known centaurs. That sounds like a lot, but it's a tiny fraction of the population. Most centaurs are too faint, too distant, or too small to be detected by current surveys. And detecting rings requires stellar occultations, which are rare events that require advanced planning and coordinated observations. We know of a few other ringed small bodies. Chariklo has 2 narrow rings. Haumea has 1. Quaoar has a ring that, like Chiron's, sits outside its Roche limit. So ring systems on small bodies are not unique to Chiron. They might even be common. We just don't know yet. But Chiron is the only one that combines rings with active outgassing. That combination is what makes it special. It's not just a ring system left over from an ancient collision. It's a living, evolving system fed by ongoing processes changing on timescales we can observe. If Chiron is representative, if many centaurs go through a ringed phase during their migration from the Kuiper Belt inward, then rings might be a transitional state, a temporary stage in small body evolution. Objects acquire rings when they first become active, when warming triggers outgassing that loft's material into orbit. Then, over time, the rings either dissipate or coalesce into moons, depending on the details of the environment. This would have profound implications for solar system formation. It would mean that satellite formation, the process by which moons accrete around planets, might be common even on small bodies. It would mean that the early solar system, when everything was in flux and objects were constantly migrating and colliding, might have been filled with ringed bodies, mini-planetary systems in various stages of formation and destruction. Chiron's volatile inventory also tells a story. The presence of CO2, CO, methane, ethane, propane and acetylene reveals something about the chemistry of the region where Chiron formed. These molecules don't form everywhere. They require specific temperature and pressure conditions, specific irradiation environments. The fact that Chiron has them suggests it formed in the outer Kuiper Belt, or even farther out, in the scattered disk where temperatures were cold enough to trap these volatiles in ice. When Chiron eventually becomes a Jupiter family comet, it will carry those volatiles with it. It will deliver them to the inner solar system, where some might even reach Earth. This is one of the ways planets acquire water and organic molecules. Comets are delivery vehicles, bringing material from the outer solar system inward, enriching planets with the building blocks of life. So Chiron isn't just a curiosity. It's a window into the chemistry of the early solar system, a laboratory for studying how volatiles are processed and transported, and a living example of the evolutionary pathway that connects the Kuiper Belt to the comets we see today. If Chiron is a failed planet, a planetary embryo that never grew large enough to become a full world, then perhaps we're watching the ghost of a moon that never formed. Or maybe we're watching that moon in the process of forming right now, assembling itself particle by particle in the rings, waiting for the moment when it finally clumps together into a coherent body. Either way, Chiron is a microcosm. It's a miniature planetary system, compressed into a space barely a few thousand kilometres across, showing us in real time the processes that shaped our solar system billions of years ago. And that makes it one of the most scientifically valuable objects we have access to, a natural laboratory unlike any other, waiting for us to unlock its secrets. Part 9. The Controversies. Impossible rings, data gaps, and competing teams. Science is messy. It's not a straight line from observation to truth. It's a back and forth, a constant negotiation between competing interpretations, conflicting data sets, and deeply held convictions about how the universe works. And nowhere is that messier than in the study of Chiron's rings. Not everyone is convinced they exist. The occultation data is compelling, sure. Multiple events, multiple chords, consistent detections of narrow features. But occultations are tricky. You're watching a star's light dim as an object passes in front of it, and you're trying to infer the structure of that object from a one-dimensional slice of data. It's like trying to reconstruct a sculpture by only looking at its shadow. You can get a lot of information, but there's also a lot of ambiguity. Some researchers argue that what we're calling rings might actually be something else. Dense shells of debris blown off Chiron during outbursts, jets of material venting from the surface, transient dust clouds that happen to be aligned along our line of sight. All of these could produce dips in starlight that look like rings, but aren't permanent structures. The problem is sparseness. Most occultations only have a few observation chords, a few telescopes catching the event from different locations. That's not enough to fully reconstruct the three-dimensional structure of Chiron's environment. You're interpolating between data points, making assumptions about symmetry, filling in gaps with models, and models can lie. If you go into the analysis expecting to find rings, it's easy to fit ring models to the data even if simpler explanations might work just as well. This is the curse of confirmation bias, and it's a real problem in observational astronomy. Once a narrative takes hold, once Chiron has rings becomes the accepted story, it's hard to step back and ask whether the data actually requires that interpretation. There's also the historical context. Back in the 90s and early 2000s, before the 2011 occultation, Chiron's activity was mostly attributed to comet-like jets. Researchers saw variability in brightness, spectral signatures of gas emission, and concluded that Chiron was just an active comet, nothing more. The idea of rings wasn't even on the table. Then the 2011 occultation happened, and suddenly rings became plausible. But some of the older generation of Chiron researchers remained skeptical. They've seen similar claims before, interpretations that turned out to be wrong, observations that looked solid until better data proved otherwise. There are also unpublished concerns, rumours circulating in the planetary science community. Some astronomers suggest there are asymmetries in Chiron's environment, longitudinal variations that don't fit symmetric ring models. If the material is clumpy, if it's concentrated in arcs rather than complete rings, that would change the interpretation entirely. Arcs are what Neptune has. Its ring system includes both continuous rings and clumpy arcs, regions where material is concentrated in specific orbital locations. If Chiron has arcs instead of rings, it might indicate a different formation mechanism, possibly related to Shepherd, moonlets or resonance effects that we haven't identified yet. Then there's the alternative model, a dust torus. Instead of discrete rings, what if Chiron is surrounded by a diffuse, donut-shaped cloud of dust, with denser regions that create the appearance of rings during occultations? A torus would be easier to maintain through ongoing outgassing. It wouldn't require the same level of confinement that narrow rings do. And it might be more consistent with the broad, extended dimming seen in some occultations. Or maybe it's a collapsing shell. Imagine Chiron experiences a major outburst, venting a huge amount of material. That material expands outward as a shell, but over time, gravity pulls it back down. During the collapse, the shell might fragment, creating denser regions that look like rings. Eventually, most of the material falls back onto Chiron, but a small fraction gets trapped in stable orbits, forming the permanent ring structures. Each of these alternatives has its own problems. Each requires different assumptions, different initial conditions, different physical processes. And right now, with the data we have, We can't definitively rule any of them out. The path forward is clear. More observations, more occultations, better multi-wavelength coverage, spectroscopic studies to map the composition of the ring material, dynamical modelling to test different formation scenarios, and ultimately a dedicated spacecraft mission that can image Chiron directly, resolve the rings with cameras, measure their properties with instruments designed for the task. But until that happens, the controversy will continue. Competing research teams will publish papers with different interpretations, conference talks will feature heated debates, reviewers will question assumptions, and that's okay. That's how science works. The truth emerges not from consensus, but from rigorous testing, constant questioning, and the slow accumulation of evidence that eventually becomes overwhelming. Chiron's mystery is real. The observations are real. But the interpretation is still up for grabs, and in some ways that makes it even more exciting. We're watching science happen in real time, watching the community grapple with an object that refuses to fit neatly into any category, watching our understanding evolve as new data comes in. That's the nature of discovery. It's messy, it's uncertain, and it's absolutely thrilling. Part 10, The Broader Cosmic Mirror. If Chiron can do this, what else can? Chiron is not alone. It's part of a growing list of small bodies that are systematically defying our expectations, forcing us to rethink what we thought we knew about how objects behave in space. Start with Chariklo. Discovered in 1997, Chariklo is the largest known centaur, about 250 kilometers across. In 2013, astronomers caught a stellar occultation and discovered something shocking. Chariklo has two narrow, dense rings. Just like that, the idea of ring systems on small bodies went from theoretical curiosity to observed reality. Chariklo's rings are stable, well-defined, and appear to be confined by shepherd moonlets, though the moonlets themselves haven't been directly detected. It's a miniature Saturn, a tiny world with its own ring system, orbiting in the same chaotic region as Chiron. Then there's Haumea, a dwarf planet in the Kuiper Belt. Haumea is bizarre for multiple reasons. It spins incredibly fast, completing one rotation every 4 hours, fast enough that it's stretched into an elongated ellipsoid shape. And in 2017, occultation observations revealed that it too has a ring, a narrow structure orbiting just outside its Roche limit. Haumea's ring is thought to have formed from a collision, debris from an impact that was launched into orbit and never coalesced into a moon. It's a different formation mechanism than Chiron's, but it shows that rings on small bodies can arise through multiple pathways. And then there's Quaoar, another Kuiper Belt object. In 2023, occultation data revealed that Quaoar has a ring located well outside its Roche limit, at a distance where the material should have clumped into a moon. Sound familiar? Quaoar is doing the same thing Chiron is doing, hosting a ring in a region where classical theory says rings shouldn't exist. So Chiron is not unique, it's part of a pattern. Small bodies with ring systems are not only possible, they're apparently common once you start looking for them. The question is, how common? There are thousands of known trans-Neptunian objects, objects in the Kuiper Belt and beyond. Most have never been observed during occultations. Most are too faint, too distant, or in the wrong part of the sky for us to catch them passing in front of a star. But if a significant fraction of them have rings, if ring systems are a common phase in small body evolution, then we've been missing a huge piece of the puzzle. Imagine this. What if every object migrating from the Kuiper Belt inward goes through a ringed phase? What if rings are a natural consequence of becoming active, of warming up and starting to outgas? The outgassing lofts material into orbit. The material organises into rings. Over time, the rings either dissipate or form moons, depending on the object's size, rotation, and activity level. If that's true, then the early solar system was filled with ringed bodies. Jupiter, Saturn, Uranus, and Neptune would have been surrounded by countless small ringed objects, all in various stages of migration and evolution. Some would collide, merging their rings into larger structures. Others would be ejected, carrying their rings with them into interstellar space. And maybe, just maybe, some of those ringed bodies delivered water and organics to the inner solar system, seeding the young Earth with the ingredients for life. This is speculative, sure, but it's testable. We can search for more ringed objects. We can model the conditions under which rings form and persist. We can simulate the migration of centaurs and test whether rings are a common outcome. Chiron is showing us that the line between categories is blurrier than we thought. Asteroid, comet, planetesimal, these are human labels, not fundamental types. In reality, objects exist on a continuum, a spectrum of properties and behaviours that defy rigid definitions. Chiron blurs that line. It's a comet with rings, an asteroid with outgassing, a planetesimal that never grew up. It challenges us to rethink our taxonomy, to embrace complexity, to accept that nature doesn't care about the boxes we try to put things in. And here's the big idea. What if interstellar visitors, objects like 2I Borisov and 3I Atlas, are the flashy distraction? What if the most scientifically rich anomalies are hiding among ordinary objects in our own solar system, objects we've overlooked because they don't have the cachet of being from another star? Chiron might not be exotic in origin, but it's exotic in behaviour. And behaviour is what matters. It's what tells us about physics, chemistry, dynamics, evolution. It's what teaches us how the universe works. So maybe Chiron isn't just the oddball. Maybe it's the Rosetta Stone, the key to unlocking a forgotten chapter of solar system history. Maybe it's showing us that ring systems are not rare treasures confined to giant planets, but ubiquitous features of small body evolution, hiding in plain sight, waiting for us to notice. If Chiron can do this, if a 200-kilometre comet can host a complex evolving ring system, then what else can? What are we missing? What other surprises are out there, orbiting quietly, waiting for the right observation, the right occultation, the right moment when we finally see what's been there all along? The universe is stranger than we imagined. Chiron is proof. And the best part, we're just getting started. Part 11. AI Breakthrough. Concept-driven law discovery. While astronomers struggle to explain Chiron's rule-breaking physics, something equally revolutionary is happening in artificial intelligence. In 2025, researchers unveiled AI Newton, an AI system that can derive physical laws from raw data without any prior knowledge of physics. Let that sink in for a moment. We've had machine learning systems that can recognize patterns, classify images, predict outcomes. But AI Newton does something fundamentally different. It doesn't just fit equations to data. It discovers the underlying concepts, the fundamental principles, the laws themselves. Here's how it works. You feed AI Newton a dataset, measurements of position, velocity, acceleration, whatever. You don't tell it about Newton's laws. You don't tell it about force, mass, or momentum. You give it raw numbers and let it figure out the rest. And it does. AI Newton rediscovered Newton's second law from noisy experimental data. It derived the law of universal gravitation. It identified energy conservation as a fundamental principle, all without being programmed with any physics knowledge. The system uses something called concept-driven knowledge representation, a framework where the AI builds abstract concepts from observations, then uses those concepts to construct mathematical laws. It's not just curve fitting, it's genuine discovery, the kind of conceptual leap that took Newton himself years of thinking and experimentation to achieve. Now connect this to Chiron. Astronomers are staring at occultation data, JWST spectra, brightness curves, trying to figure out what laws govern Chiron's ring system. They're testing classical models, finding they don't work, proposing modifications, arguing over interpretations. It's slow, painstaking work. But what if an AI Newton-style system could analyse all that data and propose entirely new governing physics? What if it could identify patterns humans haven't noticed, relationships between ring structure, outgassing activity, and Chiron's rotation that we've overlooked? What if it could derive a new law of ring stability for irregular bodies, a law that explains not just Chiron but Chariklo, Haumea and Quaoar too? That future might not be far off. AI is already transforming astronomy. Machine learning algorithms classify galaxies, detect exoplanets, predict solar flares. But those are pattern recognition tasks. AI Newton represents something deeper. AI as a collaborator in the scientific process, not just a tool but a lawmaker, a system capable of genuine discovery. Imagine uploading Chiron's entire observational record to an AI Newton descendant. Every occultation, every spectrum, every photometric measurement, hundreds of data points spanning decades. Then asking, what laws explain this? the AI might come back with something completely unexpected. A new equation that incorporates Chiron's triaxial shape, its chaotic rotation, and its outgassing in ways no human physicist has thought to combine. A stability criterion for ring particles that depends not just on distance and density, but on volatile composition, surface temperature gradients, and spin-orbit coupling. It could be right. It could be wrong. But either way, it would give human scientists new ideas to test, new models to explore, new questions to ask. And here's the philosophical resonance. Just as Chiron is forcing us to rethink the laws of ring dynamics, AI Newton is forcing us to rethink how we discover laws in the first place. For centuries, scientific discovery has been a human enterprise, driven by intuition, creativity, and hard-won conceptual breakthroughs. Newton didn't just measure apples falling, he invented calculus, reformulated the entire framework of mechanics, built a new way of thinking about motion and force. Can AI do that? Can it have genuine insights, the kind of aha moments that define scientific revolutions? We don't know yet. But AI Newton suggests the answer might be yes. And if that's true, then the partnership between human and artificial intelligence in science could be transformative. We bring domain knowledge, context, the ability to ask meaningful questions. AI brings computational power, pattern recognition across vast datasets, freedom from cognitive biases that limit human thinking. Together, we might unlock mysteries faster than either could alone. Chiron's anomalies are a perfect test case. The rings shouldn't exist. The outgassing shouldn't be that strong. The real-time evolution shouldn't be that fast. Classical models fail. New physics is needed, and maybe, just maybe, AI will help us find it. That's the synergy. As we study Chiron's breaking the rules physics, AI is breaking the rules of how we discover the rules. Both are frontier science, both are rewriting what we thought was possible, and both are happening right now in 2025 as the future of discovery unfolds before our eyes. Part 12. Quantum Materials. Update. Room Temperature Geometry Control. While Chiron defies classical orbital mechanics in space, something equally strange is happening here on Earth, in laboratories where physicists probe the quantum behavior of materials. In July 2025, researchers announced a breakthrough. They had discovered a tunable quantum metric effect in a magnetic material called terbium manganese 6 tin 6, and it works at room temperature. Quantum metric is one of those concepts that sounds abstract and mathematical, but it has real, measurable consequences. In simple terms, it's a geometric property of electron wave functions, a measure of how those wave functions are distributed in momentum space. It's part of the quantum geometry that governs how electrons respond to electric and magnetic fields, how they flow through materials, how they contribute to exotic phenomena like topological transport. Usually you need extreme conditions to observe quantum geometric effects: ultra-low temperatures close to absolute zero, powerful magnetic fields, specially engineered materials with precisely controlled properties. It's finicky, expensive, and not something you can easily turn into practical devices. But terbium manganese 6 tin 6 is different. It's a naturally occurring magnetic compound, and its quantum metric can be tuned at room temperature using modest magnetic fields. The researchers observed a second harmonic electrical response, a nonlinear effect where applying an oscillating electric field produces a response at twice the input frequency. This response is directly controlled by the quantum metric, and it can be turned on and off by changing the magnetic field. What does this mean? It means quantum geometry, something that was thought to be a laboratory curiosity, might actually be useful. Sensors, memory devices, novel computing, architectures. Applications we haven't even imagined yet. But beyond the applications, there's a conceptual parallel to Chiron. Both systems are showing us that reality is weirder than classical physics allows. Chiron hosts structures beyond its Roche limit, defying classical orbital mechanics. Quantum materials show geometric effects at room temperature, defying classical engineering constraints. In both cases, we're seeing nature do things we thought were impossible, and we're having to revise our models, expand our understanding, embrace complexity we didn't account for. Think about it this way. Chiron's rings exist in a regime where classical gravity says they shouldn't. Electrons in terbium manganese 6 tin 6 behave according to quantum geometry in a regime where classical physics says thermal noise should wash out all quantum effects. Both are boundary-pushing phenomena. Both reveal that our understanding of where quantum ends and classical begins, or where rings can exist and where they can't, is incomplete. And both suggest that nature, at its extremes, has tricks up its sleeve we're only beginning to discover. Small-scale anomalies, whether in space or in materials, are telling us that the universe is richer, more textured, more surprising than the simplified models we learn in textbooks. There's also a philosophical point here. We tend to think of space as exotic and materials as mundane. Space is the final frontier, the realm of cosmic mysteries. Materials are just stuff, things we engineer for practical purposes, but that distinction is false. Materials physics is just as frontier as space exploration. The quantum world is just as mysterious as the cosmos, and both are revealing fundamental truths about how reality works, truths that might eventually connect in ways we don't yet understand. Maybe the same mathematical frameworks that describe ring stability around irregular bodies also describe electron behavior in topological materials. Maybe there are deep symmetries, universal principles that apply across scales, from quantum wave functions to planetary rings. We don't know yet, but the fact that both frontiers are exploding with surprises at the same time feels significant. It feels like we're living through a moment of discovery, a time when multiple fields are simultaneously hitting walls, breaking through, rewriting rules. Chiron defies classical orbital mechanics. Quantum materials defy classical engineering, and both are showing us that nature, when pushed to extremes, refuses to behave. That's the lesson. The universe isn't simple, it isn't predictable, it's full of edge cases, anomalies, systems that sit right at the boundary between what's possible and what's not. And those systems are the most valuable, because they're the ones that teach us the most, that force us to think harder, to question deeper, to expand our understanding. Whether we're studying rings around comets or electrons in magnets, we're doing the same thing, probing reality's surprises, one anomaly at a time. Part 13, Ocean Science. Surprise deep Arctic warming. The surprises aren't just in space or in quantum labs, they're also under our feet, or more precisely under the ice. In 2025, oceanographers published a study in Science Advances showing that the deep Arctic Ocean is warming rapidly, and the mechanism is both unexpected and unsettling. We've known for years that the Arctic is warming. Sea ice is shrinking at alarming rates. Surface temperatures are rising faster in the Arctic than anywhere else on Earth, a phenomenon called Arctic amplification. But those changes are happening at the surface, driven by atmospheric warming, greenhouse gases, changes in albedo as ice melts and exposes darker ocean water that absorbs more solar radiation. What the new study shows is that the deep Arctic, the abyssal layers hundreds and thousands of meters below the surface, is also warming. And it's not warming because heat is diffusing down from the surface. It's warming because deep water from the Greenland basin, water that used to be cold, is now transporting heat into the Arctic Ocean's deepest layers. This is a hidden thermal engine, invisible to most observations, reshaping the thermal structure of an entire ocean basin. And we didn't know it was happening until very recently. Here's the mechanism. The Greenland basin sits between Greenland and Svalbard, a region where deep water formation occurs through a process oceanographers call thermohaline circulation. Cold, dense water sinks and flows along the ocean floor, spreading into the Arctic basin like an underwater river. This deep water forms the foundation of the Arctic's thermal structure, a cold, stable layer that has remained relatively unchanged for centuries. But over the past few decades, that cold water has been getting warmer. Climate change has altered the temperature and salinity of surface waters in the North Atlantic, and those changes propagate down into the deep ocean through complex circulation patterns. Surface warming affects where and how deep water forms. Changes in rainfall and ice melt affect salinity, which affects density, which affects how and where water sinks. Now, water that used to be near freezing is a few degrees warmer. That might not sound like much, but in the deep ocean, where temperatures are stable for centuries, a change of even 1 or 2 degrees Celsius is enormous. And when that water flows into the Arctic basin, it brings heat with it, warming the abyssal layers from below. The implications are profound. This hidden heat could destabilize long-term climate projections. Scientists have built models predicting how the Arctic will respond to warming, but most of those models focus on surface processes: ice melt, atmospheric temperature, precipitation patterns. If the deep ocean is warming from below, carrying heat that will eventually work its way up toward the surface, those models could be missing a critical component. This deep warming could affect ocean circulation patterns. The Arctic Ocean connects to the Atlantic through narrow passages, and the flow of water through those passages drives part of the global ocean conveyor belt, the system of currents that redistributes heat around the planet. Changes in Arctic deep water could ripple through the entire system, affecting weather patterns thousands of kilometres away. It could affect ice melt rates. If warm water wells up from below, it could melt sea ice from underneath, accelerating the loss of ice coverage. This creates a feedback loop. Less ice means more open water, which absorbs more solar radiation, which warms the surface, which further disrupts circulation patterns. It could affect marine ecosystems. Deep-sea organisms in the Arctic are adapted to extremely stable, cold conditions. A temperature increase of even a degree or two could push some species beyond their thermal tolerance, reshaping food webs, altering predator-prey relationships, cascading through entire ecosystems. It's a slow-moving change, but it's relentless, and it's accelerating. The deep ocean has enormous thermal inertia. It takes decades for heat to penetrate to these depths, but once it's there, it takes decades to leave. Even if we stopped all greenhouse gas emissions tomorrow, the warming already set in motion would continue for generations. Now draw the parallel to Chiron. Just as the deep ocean hides a throbbing thermal engine invisible to surface observations, Chiron hides a dynamic, active interior, not the frozen, static rock we might expect from a distant icy body. Both systems look stable on the surface. The Arctic Ocean is ice-covered, vast, seemingly unchanging to the casual observer. You could stand on the ice and never know that kilometres below your feet, the abyss is warming, heat is flowing, the entire thermal structure is shifting. Chiron is a distant comet, cold and inert by most appearances, a tiny dot of light in telescopes. You'd never guess that it's venting gases, that its interior is crystallizing, that material is being launched into orbit to form and maintain a complex ring system. But beneath the surface, both are restless, evolving, driven by internal processes that we're only now beginning to perceive. Both are systems where the action happens in the hidden places, in the depths we can't easily observe, in the interiors we can't directly measure. And both remind us that what we don't see matters just as much as what we do. The deepest parts of systems, whether oceans or comets, hold secrets. They store energy. They drive long-term evolution. And if we ignore them, if we only focus on the surface, we miss the full picture. There's also an urgency here. Just as astronomers need to coordinate occultation campaigns to monitor Chiron's changing rings, oceanographers need to deploy sensors, conduct deep-sea missions, monitor the abyss to understand climate's hidden drivers. The deep ocean is hard to access. It's dark, cold, under immense pressure that crushes most instruments and vehicles. Deploying sensors at abyssal depths requires specialized equipment, research vessels, and significant funding. Each expedition is expensive, logistically complex, and limited in scope. We have better maps of Mars than we do of the deep ocean floor. Instruments are expensive, ships are expensive, training personnel is expensive. Maintaining long-term monitoring programs requires sustained funding, political will, and international cooperation. But if we don't look, if we don't measure, we won't know what's happening until it's too late to predict the consequences. The same is true for Chiron. It's far away, faint, difficult to observe. Stellar occultations, the primary method for mapping Chiron's ring system, are rare events. They require knowing Chiron's precise position, predicting when it will pass in front of a bright star, and positioning telescopes along the narrow path where the occultation is visible. This requires international collaboration, sharing of data and resources, perfect timing, and luck with weather conditions. Coordinating occultation campaigns means getting observers in multiple countries to dedicate telescope time to a single event that lasts only seconds. It means processing data quickly, comparing results from different sites, building models to interpret the observations. It's painstaking work, requiring patience and persistence. But if we don't make the effort, we miss the chance to watch a planetary system evolve in real time. We miss the opportunity to see rings forming, changing, possibly coalescing into moons. We miss the chance to test our theories against observations, to refine our models, to understand the physics that governs these systems. Both challenges demand patience, resources, and sustained attention. Both require us to look beyond the obvious, to probe the hidden layers, to embrace complexity rather than settling for simplified models that ignore what we can't easily see. And both reveal that the universe isn't only weird in the heavens. Weirdness is under our feet. It's in the abyss, in the crushing darkness kilometres below the ocean's surface. It's in the ordinary places we thought we understood, waiting to surprise us the moment we look closely enough. The Arctic Ocean seemed stable. Scientists had been studying it for decades. The deep layers were cold, unchanging, predictable, until they weren't. Until someone looked carefully and noticed that the temperature was creeping up, that heat was flowing in from unexpected sources, that the system was changing in ways no one had anticipated. Chiron seemed simple. It was classified as an asteroid, then as a comet, then as a centaur. Problem solved, category assigned, move on. Until occultations revealed rings, until JWST revealed complex chemistry, until brightness variations revealed outbursts and activity cycles, until the full picture emerged. This isn't a simple object at all. It's a dynamic, evolving system that defies easy categorization. Chiron teaches us that small bodies are not simple. They're not just frozen relics, dead rocks preserving primordial composition unchanged since the solar system's formation. They're active, evolving, responding to internal processes we're still trying to understand. They have interiors, thermal histories, chemical differentiation. They're miniature worlds with their own complexity. The deep ocean teaches us that stable systems are not static. What looks unchanging on the surface can be in flux beneath. What seems well understood can harbour surprises. What appears simple can be complex once you look deeper. And both teach us humility, reminding us that nature's complexity exceeds our models, our expectations, our ability to predict. We build simplified models because they're tractable, because we can solve the equations, because they give us answers. But the universe doesn't care about tractability. It does what it does according to its own rules, which are often more complex, more nuanced, more surprising than our simplified versions. The lesson is clear. Assume nothing, question everything, and keep looking, because the next surprise is always closer than you think. The deep Arctic warming wasn't on anyone's radar until recently. It wasn't in the climate models. It wasn't part of the conventional understanding of how Arctic warming works. But it's real, it's happening, and it has implications we're still trying to understand. Chiron's rings weren't predicted. When the first occultation hints appeared in 2011, most researchers thought they were seeing jets or temporary shells. The idea of stable rings on a small active comet seemed implausible. But observation after observation confirmed it. The rings are real. They exist where they shouldn't, and they're teaching us that our understanding of ring dynamics was incomplete. Both discoveries came from sustained observation, from looking carefully at systems we thought we understood, from being open to the possibility that we might be wrong. That's the scientific method at its best, not defending existing theories, but testing them, probing them, being willing to revise them when observations demand it. And that's what makes both Chiron and the deep Arctic so valuable. They're not just interesting anomalies, they're teachers. They're showing us where our models break down, where our understanding is incomplete, where we need to think differently. The universe is full of hidden complexities. Some are 18 astronomical units away, in the cold space between Saturn and Uranus. Some are right here on Earth, kilometres below the surface of the ocean we've been studying for centuries. But they're all waiting, all ready to surprise us, all capable of rewriting what we thought we knew. That's the nature of discovery. It's not a steady march toward complete understanding. It's a series of surprises, moments when observation contradicts expectation, when reality refuses to fit the model, when we're forced to admit that we had it wrong. Those moments are uncomfortable. They challenge our expertise, our authority, our claim to understand how things work. But they're also exhilarating. They're opportunities to learn, to refine, to build better models that capture more of reality's richness. Chiron is giving us one of those moments. The deep Arctic is giving us another. And if we're paying attention, if we're humble enough to accept what observations are telling us, both will make us better scientists and give us a deeper, truer understanding of the universe we inhabit. So assume nothing, question everything, and keep looking, because the next surprise, the next hidden engine, the next impossible structure is already there, waiting beneath the surface, ready to rewrite the textbooks the moment someone bothers to look. Part 14, Biotech Speculation, Simulated Evolution by AI. In 2024, researchers unveiled ESM-GFP, an artificial fluorescent protein that never existed in nature. It wasn't discovered in some exotic organism deep in the ocean. It wasn't engineered through traditional genetic modification, the painstaking process of cutting and splicing DNA in laboratory settings. It was evolved in silico, created by an AI that simulated 500 million years of molecular evolution in a matter of weeks. The AI, called ESM-3, is a large language model trained on millions of protein sequences. It learned the grammar of proteins, the intricate rules that govern how amino acids fold into functional structures, how mutations affect stability and activity, how certain sequences produce certain shapes and certain functions. Then researchers used it to generate new sequences, testing them computationally, iteratively improving them through cycles of prediction and selection. The result was ESM-GFP, a protein that glows green under ultraviolet light, just like natural fluorescent proteins found in jellyfish and other bioluminescent organisms, except ESM-GFP's sequence shares only about 58% identity with any natural protein. It's genuinely novel, a product of AI-guided evolution that compressed 500 million years of natural selection into an algorithmic process that ran on computers over the course of several weeks. When the researchers synthesized ESM-GFP and tested it in the lab, it worked. It folded correctly into its three-dimensional structure. It fluoresced exactly as predicted. It was stable under laboratory conditions. A fully functional protein, designed by an AI, brought into existence through human synthesis, performing a biological function despite never having existed in any living organism. This is evolution as engineering. It's natural selection without nature. It's a process that normally takes geological timescales, eons of random mutation and environmental pressure, compressed into computational timescales, then manifested physically in the real world through chemical synthesis. Now draw the parallel to Chiron. Chiron's ring system is self-organizing. Particles collide, aggregate, settle into stable orbits, creating structure from chaos. It's a natural process governed by gravity, collisions, and dynamics. On Chiron, that process is happening in space, driven by physical forces operating over years and decades. In AI-guided protein evolution, structure emerges from simulation, from in silico dynamics, from algorithms that mimic the selective pressures of evolution. Both are systems where complex organization arises from simple rules applied repeatedly. In Chiron's case, it's Newton's laws, collision physics, and orbital mechanics. In ESM-GFP's case, it's the rules of protein folding, thermodynamic stability, and functional optimization. But here's the deeper connection. Both blur the line between natural and artificial. Chiron's rings are natural, formed by processes inherent to cometary physics. Material is vented into space through outgassing. It goes into orbit. It collides with other particles. Over time, it organizes into rings through purely physical processes. No intelligence required, no design, just the blind operation of natural law. But if we someday send a spacecraft to Chiron and intentionally seed its rings with material, using outgassing events we've predicted, timing our intervention to maximize the amount that goes into stable orbits, are those rings still natural? Or have we made them artificial? The particles would still be governed by the same physics. The orbital mechanics would be identical, but the timing, the quantity, the deliberate placement would be products of human intention. Similarly, ESM-GFP evolved through an algorithmic process that mimics nature, but the process itself is artificial. The protein is real, functional, indistinguishable from a natural one in its chemical properties. But its origin is computational. It was designed in a sense, though the design process was evolutionary, rather than deliberate blueprint drawing. This is the future, a world where the boundary between natural and artificial dissolves, where we can guide evolution, engineer planetary systems, build molecules that never existed but could have. It's not playing God, despite what some critics might say. It's partnering with the processes that have always driven complexity, but accelerating them, directing them, using intelligence as a tool to explore possibility space faster than blind chance ever could. And it raises a provocative question. If AI can evolve proteins, Can it evolve planetary systems? Can we simulate Chiron's ring dynamics, testing thousands of different initial conditions, different outgassing patterns, different particle sizes and compositions, and evolve the system towards stable configurations we could never predict? Analytically? Maybe. The computational challenge is immense, simulating 500 million years of protein evolution, where each protein is a string of a few hundred amino acids, is one thing. Simulating gravitational dynamics, collisions, and outgassing for millions of particles over thousands of orbits, where each particle's position and velocity must be tracked with high precision, is another order of magnitude more difficult. But the principle is the same. Use computation to explore possibility space far faster than nature does, then extract insights about which configurations are stable, which are transient, which are impossible. Run the simulation forward, see what emerges, compare it to observations, iterate. If we could do that for Chiron, we'd gain understanding we can't get any other way. We'd see which ring structures emerge naturally from different starting conditions. We'd identify the critical parameters that determine whether rings collapse into moons or persist indefinitely. We'd understand how outgassing frequency, particle size distribution, and Chiron's irregular gravity field interact to create the observed structures. We'd predict what Chiron will look like a decade, a century, a millennium from now. Will the rings still be there? Will they have coalesced into moonlets? Will they have dissipated entirely? Right now, we can only speculate. With sufficient computational power and sophisticated models, we could know. That's the power of simulation. It's not just modelling what exists, it's exploring what could exist, what might have existed, what will exist given different perturbations. It's evolutionary thinking applied to planetary physics, the same conceptual framework that gave us Darwinian evolution, now applied to rings, moons, and cometary systems. And here's where it gets philosophical. If Chiron is a natural laboratory showing us how ring systems evolve, our laboratories are becoming evolutionary labs too, building new matter in silico, creating molecules through simulated evolution, just as Chiron builds structures through physical evolution. Both are generative processes. Both create novelty. Both explore the space of what's possible, constrained by physical laws, but open to countless variations within those constraints. In Chiron's case, the constraint is gravity and orbital mechanics. In ESMGFP's case, the constraint is protein folding thermodynamics and the genetic code. The resonance is striking. In space, particles aggregate and disaggregate, testing configurations until stable structures emerge. Some configurations are stable, they persist, they grow. Others are unstable, they disperse, they vanish. Over time, through this process of trial and error, order emerges from chaos. In computational biology, amino acids are assembled and tested, iterating through sequences until functional proteins emerge. Some sequences fold into stable functional structures. They're selected, they're amplified, others misfold or lack function. They're discarded. Over many iterations, through this process of variation and selection, proteins with desired properties emerge. Different substrates, different time scales, but the same underlying logic: variation, selection, amplification. This is how complexity arises everywhere, from molecules to moons, and now we're learning to harness it, to guide it, to use it as a tool for discovery and creation. So when you look at Chiron's rings, you're not just seeing an astronomical anomaly, you're seeing evolution in action, planetary evolution, the slow grind of physics building structure from chaos. Every collision between ring particles is a test. Every orbital configuration that persists is a success. Every structure that forms is a solution to the optimization problem posed by gravity and dynamics. And when researchers build proteins like ESMGFP, they're doing the same thing, just in a different domain, with different tools. Every amino acid sequence is a test. Every protein that folds correctly is a success. Every functional protein is a solution to the optimization problem posed by thermodynamics and biology. It's all connected. The universe builds. AI builds. Life builds. And we, standing at the intersection of all three, are learning to build alongside them, to participate in the creative processes that have always shaped reality. This convergence is profound. For most of human history, we've been observers. We've watched nature do its thing, marveled at its complexity, tried to understand its rules. Now we're transitioning from observers to participants. We're not just watching evolution, we're guiding it. We're not just studying planetary systems, we're simulating them, predicting them, maybe someday engineering them, and this raises questions about agency, about intentionality, about what it means to create. When ESMGFP glows green in a laboratory, who created it? The AI that generated its sequence? The researchers who trained the AI and synthesized the protein? Evolution itself, operating through an algorithmic substrate? Or is the question meaningless, a category error that assumes creation requires a single creator rather than a collaborative process between intelligence, computation, and physical law? Similarly, when Chiron's rings organize themselves into stable structures, is that creation? Is it design? Or is it just physics doing what physics does, operating blindly according to mathematical rules, producing organization without intention? Maybe the distinction doesn't matter. Maybe what matters is the outcome: complexity emerging from simplicity, structure arising from chaos, novelty appearing where none existed before. Whether that process is natural or artificial, guided or blind, intentional or automatic, the result is the same. Something new enters the world. Chiron is humanity's mirror, showing us that nature's weirdest tricks are not only out there in space, but unfolding all around us in every domain. Where complexity emerges from simplicity, where structure arises from chaos, where the possible becomes actual through the relentless iteration of physical law. When we study Chiron, we're studying how matter organizes itself in the absence of life, intelligence, or design. When we build proteins with AI, we're learning how intelligence can accelerate those same organizational processes, compressing timescales, directing outcomes, exploring possibilities faster than blind chance ever could. Both teach us about emergence, about how the universe generates novelty. Both reveal that creation isn't a single act, but an ongoing process, happening everywhere, all the time, at every scale. And both suggest that the future of science isn't just understanding nature, it's partnering with nature, collaborating with the creative processes that have always been there, using our intelligence and our tools to explore what's possible and bring new possibilities into being. That's the synthesis. Chiron shows us evolution in space. ESMGFP shows us evolution in computation. Together, they show us that evolution is universal, a fundamental principle of how complexity arises, whether in proteins, particles, or planetary systems. And we're just beginning to grasp the implications of that universality, just starting to see how the same frameworks apply across domains, just learning to use those frameworks as tools for discovery and creation. The universe has always been creative. Now, we're learning to be creative alongside it. That's the lesson. That's the future. And it's unfolding right now, in laboratories on Earth, and in the cold darkness 18 astronomical units from the Sun, where Chiron tumbles through space with its impossible rings, quietly teaching us how worlds are built. Part 15. Fundamental Physics, Mathematical Limits on the Simulation Hypothesis. We're going to end where all great mysteries converge, at the boundary between physics and philosophy, where mathematics meets metaphysics, where the question isn't just what is Chiron, but what is reality. In 2025, a team of physicists published a proof claiming that the universe cannot be a simulation. Not in the sense that it's unlikely or improbable, but in the sense that it's mathematically impossible for a completely algorithmic computational model to fully capture physical reality. Their argument is rooted in Gödel's incompleteness theorems and the concept of undefinability. Here's the essence. Any formal system powerful enough to describe arithmetic contains statements that are true but unprovable within that system. There are mathematical truths that cannot be derived algorithmically, that require stepping outside the system, invoking concepts or axioms that the system itself cannot generate. If the universe were a simulation, it would be a formal system, a set of rules executed by some computational substrate. But formal systems are fundamentally limited. They cannot capture everything. There are aspects of reality, the researchers argue, that are non-algorithmic foundational elements that cannot be reduced to computation. Therefore, if physical reality contains non-algorithmic aspects, and if our best mathematical understanding suggests it does, then the universe cannot be purely computational. It cannot be a simulation in the sense that simulation hypothesis proponents imagine. Now you might be asking, what does this have to do with Chiron? Everything. If our universe isn't just a program, if there are non-algorithmic emergent aspects to reality, then anomalies like Chiron aren't glitches. They're not bugs in the code. They're features of a genuinely complex, non-reducible cosmos. Chiron defies simple models. Its rings exist where they shouldn't. Its activity follows patterns we don't fully understand. Its evolution happens on timescales that seem too fast, too dynamic, too rich for the simple equations we try to apply. Maybe that's because reality itself is richer than any simulation could be. Maybe the universe is fundamentally surprising, not because we haven't found the right algorithm yet, but because no algorithm can capture it. This connects to everything we've talked about. Quantum materials showing geometry at room temperature, deep oceans hiding thermal engines, AI evolving proteins, Chiron hosting impossible rings. None of these fit neatly into the simplified models we built when we thought the universe was clockwork, predictable, reducible to equations. But the universe isn't clockwork. It's fluid, emergent, creative. It generates novelty. It explores possibility space. It builds structures that surprise even the physicists trying to explain them. And that's liberating. It means science isn't closing the book on mystery. It's writing new chapters. Every anomaly, every surprise, every object like Chiron that refuses to behave is evidence that we haven't reached the end of discovery. We're nowhere close. The implications of this non-algorithmic reality extend far beyond philosophical debates. They touch every mystery we've explored in this journey through Chiron's impossible world. When we observe rings that shouldn't exist beyond the Roche limit, when we see outgassing driven by mechanisms we're still trying to understand, when we watch structures evolve on timescales that seem impossibly fast, we're witnessing the universe doing what it does best, surprising us. Think about what this means for our understanding of physical law itself. For centuries, physics has been built on the assumption that if we just find the right equations, if we just build powerful enough computers, we can predict everything. We can simulate any system, model any process, calculate any outcome. The universe, in this view, is deterministic, mechanical, knowable. But Gödel showed us that mathematics itself has limits. There are truths that cannot be proven within any formal system. There are statements that are true but unreachable through algorithmic processes. And if mathematics, the language we use to describe reality, has these fundamental limits, then perhaps reality itself is not fully capturable by computation. This doesn't mean physics is wrong or that equations don't work. They do. Spectacularly well in most cases. But it means there's something deeper, something that escapes pure algorithmic description. And when we look at Chiron, at its chaotic rings and unpredictable outbursts and real-time evolution, we might be seeing glimpses of that deeper reality. Chiron sits out there, 18 astronomical units from the Sun, tumbling through space with its impossible rings, venting methane and propane into the void, quietly evolving in ways we're only beginning to perceive. It doesn't care about our theories. It doesn't care about Roche limits or shepherd moons or whether rings should exist on small bodies. It just is, and in being it challenges us. It dares us to look closer, to question harder, to abandon assumptions that constrain our thinking. Consider what we've learned just in the past few years. The 2022 occultation showed a broad disk plus ring concentrations. The 2023 multichord observation resolved 3 distinct rings and a faint outer feature. JWST spectroscopy revealed a surface rich in volatiles we didn't expect to find there. Methane fluorescing in non-local thermal equilibrium, carbon dioxide and methane venting from different regions, an outburst in 2021 that injected fresh material into the system. Each observation adds another layer of complexity. Each dataset raises new questions, and crucially, each surprise suggests that our models, no matter how sophisticated, are missing something fundamental about how these systems work. That's the message of this entire story. From Chiron's rings to AI discovering physical laws to quantum materials, to deep ocean heat to simulated proteins to mathematical proofs about the nature of reality. We're living through a moment when surprises are everywhere. The universe, at every scale, is showing us that it's deeper, stranger, and more alive than we dared imagine. We thought interstellar comets were the exotic visitors, the objects that would teach us about other star systems, other chemistries, other worlds, and maybe they will. But the strangest comet, the one with the most to teach us, was here all along. We just weren't looking. Chiron is not the outlier, it's the teacher. It's the Rosetta Stone for a forgotten chapter of solar system evolution. the key to understanding ring formation, satellite accretion, volatile transport, all the messy, chaotic processes that shaped our cosmic neighbourhood billions of years ago and continue shaping it today. And here's the beautiful irony. In teaching us about ring systems and small body dynamics, Chiron is also teaching us about the nature of scientific discovery itself. It's showing us that progress doesn't come from fitting observations into existing frameworks. It comes from letting observations shatter those frameworks, from being willing to admit that what we thought we knew was incomplete. The classical Roche limit model says rings can't exist where Chiron's rings are. But they do. So either the observations are wrong, which multiple independent datasets now make unlikely, or the model is incomplete. And if the model is incomplete for Chiron, where else is it incomplete? How many other small bodies are hosting rings we haven't detected yet? How many Kuiper belt objects, centaurs, asteroids might be surrounded by structures we never thought to look for? So while the world chases headlines about interstellar visitors, remember the lesson of Chiron. The most profound mysteries are often hiding in plain sight, orbiting quietly, waiting for the moment when someone looks closely enough to see what was always there. Reality is not a simulation. It's not a program. It's an unfolding, an emergence, a constant generation of novelty from the interplay of physical law and contingent circumstance. And we, as observers, as scientists, as curious beings trying to understand our place in this vast cosmos, get to participate in that unfolding. Every observation is an act of discovery. Every anomaly is an invitation. Every mystery, from Chiron's rings to the quantum metric to the deep ocean's hidden heat, is a thread we can pull, a question we can ask, a path we can follow toward deeper understanding. The universe isn't done surprising us. It's just getting started, and so are we. In the coming years, more occultations will refine our picture of Chiron's ring system. JWST will continue monitoring its outgassing, tracking changes in composition and activity level. Dynamical simulations will become more sophisticated, incorporating better models of Chiron's irregular shape and chaotic rotation. And eventually, perhaps within our lifetimes, a spacecraft might visit, imaging the rings directly, measuring their properties up close, maybe even discovering those elusive shepherd moonlets. Each of these future observations will either confirm what we think we know, or surprise us again. And honestly, the surprises are more valuable. They're the ones that push science forward, that force us to think differently, that open new avenues of investigation we never considered. Chiron waits out there, in the cold and the dark, defying expectations, evolving in real time, challenging everything we thought we knew about how small bodies work. It's not the end of the story, it's the beginning. So pay attention, keep watching. Because the next surprise, the next impossible object, the next rule-breaking anomaly is already out there, orbiting quietly, waiting for someone to notice. And when you find it, when you see something that shouldn't exist but does, remember Chiron. Remember that nature doesn't follow our rules. We follow nature's, and nature's rules are far stranger, far richer, far more beautiful than we ever imagined. That's the universe we live in. Surprising, mysterious, endlessly creative, and absolutely, undeniably, wonderfully real. The journey from Chiron's discovery in 1977 to today's sophisticated understanding spans nearly 5 decades of patient observation, careful analysis, and willingness to be surprised. Charles Cowell looked through a telescope and saw what he thought was an asteroid. Decades later, we're still trying to figure out what Chiron actually is. That's not a failure of science. That's science working exactly as it should, constantly refining, constantly questioning, constantly open to new information that changes the picture, and the picture keeps changing. Every few years, another occultation, another spectrum, another outburst, another piece of data that doesn't quite fit the models. Chiron refuses to be understood easily, and in that refusal, it's teaching us something profound about the nature of understanding itself. We don't understand things by forcing them into categories. We understand them by observing carefully, by being humble enough to admit when our models fail, by building new frameworks that accommodate what we actually see rather than what we expect to see. Chiron is giving us that opportunity. It's forcing us to build new physics, to think creatively about ring confinement mechanisms, to consider multiple engines of activity working simultaneously, to embrace complexity and real-time evolution in ways that planetary science has rarely had to do. And in doing so, it's reminding us why we study space in the first place. Not just to catalogue objects or confirm theories, but to be amazed, to confront the unknown, to stand at the edge of what we understand and peer into what we don't. That's where Chiron sits, at the edge, 18 astronomical units out, in the zone between order and chaos, between the familiar and the strange, between what textbooks say should happen and what actually does. It's the perfect symbol for 2025 science, rule-breaking, surprising, impossible to ignore, and absolutely essential for anyone who wants to understand how our solar system really works. The cosmos isn't a museum, it's a laboratory, and Chiron is one of its most active experiments, running in real time, changing before our eyes, daring us to keep up. So here we are, at the end of this exploration, and the only honest conclusion is that we're really at the beginning to understand Chiron, beginning to grasp the implications of its rings, beginning to see how many other mysteries might be hiding in the spaces we thought we'd already explored. The universe is speaking. Chiron is one of its voices. And if we listen carefully, if we set aside our preconceptions and let the observations guide us, we might just hear something that changes everything we thought we knew about how worlds, rings and moons come to be. That's the promise. That's the invitation. That's why Chiron matters more than any interstellar visitor ever could. Because it's not about where something comes from. It's about what it teaches us. And Chiron has lessons we're only beginning to learn.